So I decided what I want to do today is I want to review very quickly the materials from chapter 2 and chapter 3 up to the point that things are included in the midterm, so that it gives you a little bit of quick start on preparing for the exam. I know you have already been preparing, but I want to give you one very quick summary in 1 hour, and hopefully that makes you have a better overview of the material. Okay, so what I want to do is that I will be going through topics relatively quick. I won't be doing any specific example because we don't have time to do examples. It's the whole chapter 2 plus most part of the chapter 3, but I will mention some of the examples that are useful, and I will mention how you should think about them and how you should approach them. Okay, then I will let you work on the rest. Okay, so that's the plan for today. And then if you have any further question this evening, tomorrow, you can always email me, and I try to answer by email. If it's too long, not by email, we can set up an online chat sometime. We can set that as well, okay? And if you have any questions or problems on the assignments, you can contact Jocelyn, the TA of the course as well. Sounds good? So let's get started, okay? And then we go step by step. Okay, so I list topics from chapter 2 here on the board. Okay, so from chapter 2, we're going to look at electric field, Coulomb's law, divergence of E, which leads to the Gauss law. Curl of E is 0. That's why we can define electric potential, work on energy and conductors and capacitors. Okay, so to start with, if we have a test charge, let's say capital Q, and we have a charge here Q, you know the force between these two is defined by the Coulomb's law, 1 over 4 pi epsilon 0 Q times R squared. R here is distance vector, and this is times R hat, means the direction of the force is exactly in the same direction that you connect these two. Okay, so this is a force between 2 point charges, right? And then we talked about superposition principle always being correct when you have multiple point charges, and if you're trying to calculate the field between them. That means if here, let's say we have multiple charges, okay, let's say Q1, Q2, and so on, then this force from particle number I on charge Q is Qi times Q over Ri squared. Okay, so this is the force between each of these point charges on the test charge Q. Okay, and if we want to look at the total force on the charge Q, we can just add them up. okay? Like adding vectors, sigma I from 1 to n, qi, q, ri, r hat, okay? So multiple charges, you just add the forces. Okay, and what's nice about this is that this force at the end of the day is proportional to Q. So you can write it in terms of 1 over 4 pi epsilon 0 Q, the magnitude of the electric charge on the test charge times sigma I from 1 to n Qi Ri times R hat, okay? So basically, whenever you have any charge Q, okay, in a space, the force, the electric force on this is always proportional to the charge of Q, okay? So the force on charge Q is always proportional to Q, the magnitude of the electric charge on it, okay? So that's why people define electric field that quantifies the strength of the force that could be exerted on an electric charge. Okay, so the force, let me erase this part. So this is proportional so that you can write F on Q in terms of the charge Q times electric field. The force is a vector, has direction, so that electric field is a vector as well. Okay, so how do you define electric field? This is basically how you define electric field from this equation. Okay, so if you look at this, and if you take Q out of the equation, what is remaining is the electric field created by all these point charges. Okay, so electric field from all these point charges at any point in a space is 1 over 4 pi epsilon 0 sigma qi ri. By the way, this is ri square and this is ri square. Okay, I missed the power of 2 here and here. Please correct that in your notes. So ri square times r hat. This is how you can calculate electric field in a very direct manner created by multiple point charges, okay? So Ri, remember, is a distance vector and R is a position in the space, okay? So basically this is the location R and Ri, each of them is distance vectors like this. Sounds good? So this is how you can find electric field of the point charges in a very direct way. Okay, and multiple times in this course, I reminded you and I emphasized you that the main mission of electrostatics is basically this one, calculating electric field that is created by certain charge distribution. Could be random charge distribution, not necessarily point charges. A lot of times, the point charge is, point charge is a limiting definition of very, very small sphere. Okay, so in terms of electrostatics, you should think about you have random charge distribution, continuous charge distribution on a space, on a surface, or on a line, and then you want to calculate electric field. That itself is not an easy problem, okay, and that is the mission of electrostatics. Electrodynamics looks at different things, but electrostatics is this. So this, looking very simple equation, but this is the base of what we're gonna work with, okay. Now, calculating these for point charges may be easy, for continuous charges can be difficult, especially if there is no specific nice symmetry in the problem, okay? So basically, chapter 2, we're gonna look at these things, we're gonna look at different methods to find electric field, and chapter 3 focuses on one of the methods, which is focused on electric potential, okay? So this is just to, again, give you one overview. Okay, so this is electric field from point charges. What if we have a continuous charge distribution? Okay, let's forget about these point charges, but let's imagine we have one random shaped material and then we have charge density inside this as well, maybe some surface charges as well. Okay, so how do we calculate electric field created by this one? This discrete type equation can be written in terms of continuous charge distribution. Okay, so for that matter, E of R, you can change this summation into an integral. So we have the same factor, 4 pi epsilon 0. Now we have an integral of 1 over R squared times R hat. Okay, so 1 over R squared is the denominator here. R hat is this R hat here. But instead of Qi, we will have dq, meaning that infinitesimal small charge that are creating the whole charge distribution up here. Okay, so what is dq? Then it depends what type of charge distribution you have. Okay, so we previously looked at this and said if we have a volume charge density, okay, with rho at any position, okay, we can look at very small. Of course, I'm exaggerating the size here. And here, dq, but I don't need to have this arrow. I'm going to write below this. So here, dq is rho times d thou. Sounds good? And then if we have surface charge, okay, we can look at a small area, dA. In this case, the volume was d thou. And here, for a surface charge, dq is sigma, the surface charge density times dA. Okay, and if we have line charge distribution, okay, we can look at a small piece with the length of dl. Here, dq is lambda dl. Okay, so dq, infinitesimal charge here, can have different meanings depending on what type of charge distributions we have. Sounds good? So this is, again, a fundamental equation calculating electric field in terms of an integral. I would call it, it's more or less a direct way of calculating electric field. Okay, and sometimes it's doable to carry out this integral if we have nice symmetry. Okay, we have done that before. I'm going to give you a couple of examples. You can really do this. But again, this is not always feasible in a mathematically tractable way. Okay. Okay, I see a lot of chat messages here. Going in and out. Okay, is it okay? The quality is fine now?
Yeah, it was fine. I just didn't want to interrupt you if it was only my connection.
Okay, okay. So, by the way, I'm recording as well. I'm hoping to upload it quick. It takes time, but hopefully later on this evening you will have access to this. And that's going to be high definition. Sounds good? Any questions so far? So things I'm covering here should be very, very clear for you. If it's not, that means you're going to really study so that these things are by now clear for you. Okay, so there are examples of cases that we could really do this integral, okay? And these are cases that either there's a special symmetry or the geometry is simple, okay? So out of those cases, I can remind you of example 2.2 from the textbook. Okay, and the goal was calculating electric field above a uniform linear charge distribution with very specific lengths. Okay, so from minus L to plus L, there's a charge distribution here, and the question was, what is the electric field up here at the distance z from the center of the charge distribution? Okay, so in this case, we can really do this integral. Of course, you want to be careful finding what is the distance vector, what is the dq, and what is the actual dimension and direction you're carrying out the integral. Okay, For instance, here, if you want to do this integral, dq is a line charge distribution. Okay, so you're going to look at this. You have uniform linear charge distribution times dl. What is dl? dl is a small infinitesimal length here. If this is x-axis, dl should be dx. So dq is lambda dx. Okay, and you have to carry the integral from this point, positive L to negative L, or vice versa. Okay, so the integral runs over this length. What is the distance vector here? R squared. The distance vector is basically the distance from any point on this line to the point that you're calculating electric field at. Okay, so this is R. Okay, and if you think about this, if this is Z, and here, if this is X, okay, R squared is Z squared plus X squared. Sounds good? So if you want to carry out this integral, E at position, I would say E at point P should be the integral of 1 over 4 pi epsilon 0. So now we have 1 over R squared, which is this. So the integral of 1 over Z2 plus X2. And then we have R hat, which by the way is, so R itself is Z times Z hat, which is this vector minus X times X hat, which is this vector. Okay, so R as a vector is Z times Z hat minus X times X hat. Okay, and that makes R hat equal to Z times Z hat plus, minus X hat divided by a square root of Z squared plus X squared, which is the length of R hat, okay? And then dq is lambda dx, so we have lambda dx at the end, okay? The limit of integral is on x, so it should run from negative L to positive L. Sounds good? So the first steps in this type of problems is that identify what is dq, identify what is distance, and identify what is the distance vector, and then you can calculate the unit vector, okay? So you should look at the geometry where you will analyze what you have, where you are taking the integral on and everything, figure out this part, okay, all these variables, and then plugging back to this equation, okay? Don't start directly from this, okay? Then you're gonna make mistakes on what should be dq, what should be r. Try to first really figure out what geometry is telling you in terms of the dq, distance vectors, and unit vectors. Sounds good? And then there are different problems of the same type. This is in one dimension. There are examples. So I let you continue this, okay? This example from the book, I don't want to do the rest, it's in the book already. But there are different type of problems of the same nature, okay? So there is another problem as you have a disk. This is similar to the quiz problem you had, okay? But you can basically even do this directly by looking at the electric field. So you have a disk of, let's say, radius r, and then you are trying to calculate electric field right at this point. Of course, one approach is calculating electric potential. I'm going to talk about that later. But you can always do the direct integral. You can find a dA, a small volume, a small surface area here, and then see what electric field this part is creating at this point, and integrate that over the whole surface here. So for this one, you need to use spherical coordinates, polar coordinates, and do the integral on the surface of this disk, okay? Or another type of problem could be just one ring, not the disk. Sounds good? Okay, so remember, read the problem very carefully, analyze the geometry, and then start doing the integral. Sounds good? Okay, so this is one way. As I said, this is a direct way of measuring and calculating E. There are different tricks, okay? And another way is looking at the divergence of E and then using the Gauss law. Okay, so I'm going to quickly review that as well. So I'm done with this part, and now I'm moving on to the next topic. If you have questions, stop me.
Professor, I have a question about the midterms on Thursday.
Mm-hmm.
So, is it going to be like a take-home, or are you going to put it up on Critic?
It's more like take-home, but you have an hour, 15 minutes to do it.
Oh, okay.
You
so
don't
are you
record
gonna,
your voice, okay? You just do the problem, take picture, and send it to me. Email is
within
fine.
an hour?
Yes, email is fine.
Okay.
Unless if you find really you wouldn't, okay? But if you find yourself having like 10 pages of solutions and email is too big, and if you find it too big, then Dropbox link is fine as well.
So you're going to send us the question like during class hours?
Yes, so on Thursday morning, I'm gonna 9:30 in the morning, I'm sending you a PDF, emailing everyone a PDF. And that has 3 questions. So technically, if you do them right, it shouldn't take more than 3 pages.
Okay. So they're going to be 3 questions.
And you have an hour, 15 minutes. I'm here as well, so you can ask questions. You can have private chat with me here on the screen, or if there is any hint I need to give everybody, I give this. So you guys need to be online. Okay.
So we all have to join Zoom?
Pardon me?
So we all still have to join Zoom on
Yes,
Thursday?
we have Zoom the way we have it right now on Thursday as well. But you are focused on doing your exam, and I'm just here to answer any question you might have.
Okay, all right. Thank you.
Sounds good?
I have a question.
Sure.
So for the midterm, are you going to tell us the relevant equations? Are we expected to find them? Or like say...
Open book, you're at home, okay?
So what would you say, like, problem 2.1?
Okay, I don't tell you which equation to use for any problem, okay? So I let you figure that out, which equation, but you don't need to memorize an equation because you have the book with yourself.
Okay. Thank you.
Yeah, don't memorize. It's open book, open access. The problems I'm giving you might be similar to the, actually they are similar to the examples, and mostly similar to the examples I did in classroom, but those problems, I'm making them up. So hopefully you can't Google on internet and come up with answer. But you have access to your textbook and you can look at the examples, you can look at the equations. You shouldn't talk to each other, okay? Of course. And if you do that, I will figure out by the way the solutions are so similar to each other, but don't do that. Just try to work it on your own. And then you don't have much time to do that either. So focus and consult with your textbook, that's fine. Sounds good?
Professor.
And of course, I'm here too, so you can ask me questions if you really need to.
Professor, how many questions will there be on the exam?
3.
Oh, okay. Thank you.
Sounds good? Excellent. So, okay, let's move on to the next topic. Divergence of E okay, so the Gauss law says that if you choose any random volume in a space, okay, and this volume, you can define a closed surface encapsulating this volume. And the Gauss law says that any integral of E electric field dot dA on the surface of this volume should be equal to 1 over epsilon 0 times Q enclosed. And Q enclosed is the total charge enclosed in this volume. Okay, so the integral of E dot dA, and that integral runs over the whole surface of this. I put the circle sign here because it's a closed surface. Okay, and that is equal to 1 over epsilon Q enclosed, and this is the integral form of the Gauss law. This is the Gauss law in integral form. Okay, and then if you look at the divergence of E, so basically this integral can be written in terms of the divergence of E d tau integral over volume. Okay, so this is a divergence theorem. You have E dot dA, this is equal to the divergence of E dot d tau over the volume. And the Gauss law says that it's equal to 1 over epsilon 0 Q enclosed. And that Q enclosed can be written in terms of the integral of the charge density over the same volume. Okay, so here we get 1 over epsilon 0 integral of rho d tau over the same volume. Now, if you compare the first term and the last term, what do you get? You have integrals on the same volume. Okay, if that's correct, then the integrands should be equal. That means that the divergence of E should be equal to 1 over epsilon 0 times rho, and this is the Gauss law in differential form. Sounds good? Okay, so Gauss law is useful because a lot of times if you want to use it, and I can tell you most of the time you use this one if you're doing anything analytical. This is useful for calculating E in special cases that we have nice symmetry. So we don't need to go through the burden of the integral. A lot of times this integral can be nicely calculated by just looking at the geometry and integrating over specific surfaces that the magnitude of E is constant, okay? And if you do that, and for such symmetric cases, the Q enclosed, the charge density can be also calculated relatively easy so that we can calculate electric field without going through the burden of doing the integral over specific charges, okay? So there are some examples that the Gauss law is super useful. One of the examples I can give you is I'm not sure if this example is in the book, but this is one of those classic problems. It's a solid sphere, uniform charge density, okay? So you can imagine that you have a solid sphere with uniform charge density of rho, and someone asks you, what is the electric field inside, maybe here, and outside this solid sphere, okay? We did a number of examples similar to this. I hope that you already know that if you have a charged sphere, the electric field outside is very similar to the electric field created by a point charge carrying the same amount of total charge, okay? But with the Gauss law, we can relatively easily calculate that one, okay? So if you want to look at the electric field here at distance r from the center of this uniformly charged sphere, you need to look at the Gaussian surface, which is a sphere and has the same radius as a distance we are calculating electric field at. And if you look at that, the integral of E dot dA is simply E, the magnitude of electric field at R, times 4 pi R squared. This magnitude remains constant because of the symmetry of the problem. You know that if you move from this point to this point, the direction of the electric field does change, but the magnitude does not change because of symmetry. So the integral of E dot dA becomes ER times 4 pi R squared. And then if you look at the total charge enclosed in this big sphere, what is that amount? That is actually the total charge on the charge sphere, which is the rho, uniform charge density, times the volume, which is 4 by 3 pi r cubed. The r here is the radius of the solid sphere, and the r here is the distance at which you are calculating electric field. Okay, so with approaches like this, you can easily look at the magnitude of the electric field, which is 4 pi cancels out here with this. And the electric field becomes rho R3 divided by R squared. And that is, in fact, by the way, I'm missing 1 over epsilon 0 here. So this should have 1 over epsilon 0 factor here as well. So we get epsilon 0 here, and that is in fact equal to 1 over 4 pi epsilon 0 Q total, which is the total charge on the sphere divided by R squared, very similar to the electric field created by point charge, okay? Now, if you want to look at the electric field inside this solid sphere, okay? You do the same approach. The only difference is that the electric field, the total charge you're calculating, doesn't run over the whole volume of the solid sphere. It only includes the part of the sphere which is inside your Gaussian surface. Okay, so for problems like this, here, I'm just erasing this and correcting it for the case that we're looking at the electric field inside. Okay, so I'm going to erase this one. And so here we have the same terms, 4 pi r squared. So the left-hand side of the equation has exactly the same form. The right-hand side, instead of looking at the total charge and total volume of the solid sphere, I'm going to only look at the part of the solid sphere which is enclosed inside the Gaussian surface. And that is 4 over 3 pi a small r cubed. Okay, so if you look at this, then the 4 pi cancels out, r squared cancels 12 the components here, exponents here, you get r, and ER is 1 over epsilon rho r divided by 3. This is linear in terms of r. Okay, so basic idea, in cases that you have a special symmetry, you can do this integral relatively easy, okay, by knowing how the magnitude of the electric field changes, and most of the case, the magnitude of the electric field does not change, okay? And then calculating enclosed charge is relatively easy. You just need to be very careful about what geometry you are working with, okay? So examples similar to this with different geometry are cases that you have cylindrical charge distribution and you are trying to find the electric field inside and outside that cylinder, okay? Sometimes you have just line charge distribution, okay? And you're trying to calculate electric field. The same concept. Look at the geometry, define the Gaussian surface, that's the most important part, okay? You have to choose that wisely so that you can do this integral, okay? And then just follow this. Sounds good? So we looked at the Coulomb's law, to calculate electric field. We look at the divergence of E to calculate electric fields. Each of these methods are useful for certain problems, but they can be difficult for certain other problems. The next thing we're going to look at is that we're going to look at the curl of the electric field, which is 0, and based on that, we can define electric potential, which is a way to calculate the electric field. Okay, so any questions so far? I'm trying to rush a little bit because I want to make sure we cover everything here and a couple of things from chapter 3 as well, okay? So the curl of electric field, we look at that and that's 0, okay? And that is equivalent to saying that any integral on a closed surface, okay, of E dot dl is always 0, okay? On any closed loop, if you integrate E dot dl, you start from this point, okay? And you go step by step. If you look at the integral of E dot dl, that's always 0, okay? So because that's correct, we can define electric potential this way, where V at R, electric potential is a scalar function. It's function of 3 variables, but itself is a scalar, as opposed to electric field that is a vector function. Okay, we can define it as negative of integral of E dot dl from certain origin. This could be infinity for a lot of cases to the position R. Okay. We define electric potential at any point based on this, okay? And that means that if you're moving from one point in space A to another point B, the difference in the potential at B minus VA, the difference between the potential between the two is negative of the integral E dot dl moving from A to B, okay? And with this definition, if you look at the differential format of this specific equation, we can say that the electric field should be negative of the gradient of V. Sounds good. So these are the basic definitions of the electric potential. Okay, and why is electric potential useful? Mainly because it's a scalar function. Calculating electric field is a lot easier than directly calculating electric. Calculating electric potential is a lot easier than calculating electric field, okay? But as soon as you find the electric potential, you can take the gradient of that and then you can calculate electric field. Okay, so this way you're making the problem a lot easier. Okay, so these are the basic definition, but what if we have a charge distribution? How do we calculate electric potential for that? Okay, so for that, let's look at the electric potential created by a point charge, and then we're gonna extend that and see how that electric potential of a random charge distribution can be computed. Okay, so let me get rid of this and this. I'm gonna keep the last line here. So if you have a point charge, Q, okay, we already know what is the electric field at distance r created by this. Okay, so we can calculate what electric potential we have. Okay, here we make the assumption that Our origin reference is at infinity. That's where the electric potential is 0. Here, if we do the integral, negative integral of E dot dl from infinity to position R, we find that electric potential is 1 over 4 pi epsilon 0 Q, the charge of this divided by R. And R here is the distance from wherever we are calculating potential to the point charge we have. Okay. And because the superposition principle works at E, the superposition principle should work for electric potential as well. That means that if we have multiple charge distribution, Q1, Q2, and so on, and if we want to look at the electric field at this point, okay, we can just add this up. Because electric potential is a scalar, we can just algebraically add them up here. And that's really convenient compared to the way we could calculate electric field. Electric field was vectors, so we had to add vectors. Here we're just adding numbers. Okay, so V at R created by multiple charge point charges can be written as 1 over 4 pi epsilon 0 sigma Qi over, here I want to write it Ri so that it's the distance vector from each of these point charges to where we are, and I is from I to N. Okay, so this is electric potential created by a collection of point charges. Now you can imagine if instead of point charges, we have a localized charge distribution, continuous charge distribution, we can change this to the integral form. V of R is 1 over 4 pi epsilon 0 integral of dq over R. Okay. Again, you remember dq, if you have volume charge distribution, you can look at the volume elements, and dq should be rho times d thou, and that makes the whole integral 1 over 4 pi epsilon 0 rho over R d thou. Okay. And you know, if you have surface charge distribution, dq becomes sigma dA. And that is a question you had in the second quiz, right? You had a disk surface charge distribution and you calculated the electric potential by carrying out basically this integral over the surface. Sounds good? Good, okay. So the example was in the book? The one I just said for the sphere? Looks like.
Yeah, I think so.
Oh, okay. So one example of calculating this is example 2.8. Okay, so this is a little more complicated than what you had in the midterm. You have a spherical shell. This is more like an egg. Okay, so you have a spherical shell. You are trying to calculate the electric potential here. Okay, so again, one of those cases that you should really first focus on the geometry and what you have and where you want to carry out the integral. If you have a spherical shell, okay, and you're trying to find the potential here, using this integral, you should integrate over the small areas on the surface of the sphere. Okay, so you want to really look at the dAs, this infinitesimal area on the surface of the sphere, on the shell. Okay, so and that's defined by R2 sine theta d theta d phi. These are all spherical coordinates. okay, with the constant R, just changing the angle so that you can cover the surface of the shell, okay? And if you integrate over this, you should also look at the R's that are the distance from this point to where you are calculating electric field, okay? So this is example 2.8 of the textbook, okay? I suggest you review this and read this in details, okay? So that you practice how you can look at the geometry, define your integral parameters and integrands, okay? The concept is similar to what you had on quiz number 2, okay? The concept is very similar, the geometry is different, so the calculus you are doing here might be different. The physics is relatively the same. Sounds good? Any question? So from chapter 2, we also had a topic on boundary conditions, okay? So I'm not gonna review that here, but I hope you really care about how electric field is discontinuous on the surface and how electric potential is continuous, okay? Electric potential is always continuous when you are passing surfaces, okay? But electric field is not, okay? As an example, so I'm moving to the next topic quickly, okay? So as an example, if you have a surface that carries electric charge, let's say surface charge density of sigma, sigma doesn't need to be uniform, okay? As long as you have surface charge density, then you can look at the surface, let's look at the cross section, that's easier. Okay, you have the surface, and you can look at the electric field above the surface. Here above, we can look at the electric field below the surface. Okay, no matter how close you are to the surface, these two electric fields does not need to be similar to each other. They can be discontinuous, meaning that below the surface, you can have one electric field, okay? And as soon as you jump above the surface, direction can change completely, okay? And that's because the surface itself is creating electric field that is diverging or converging to the surface, okay? And that creates discontinuity in the electric field, okay? Now, if you look at that discontinuity, there's always a specific pattern. If you look at the parallel component of the electric field above, that should be equal to the parallel component of the electric field below the surface, okay? So the parallel components are always similar to each other. Surface cannot create discontinuity in the parallel component of the electric field, okay? And by that, I mean parallel to the surface. But the perpendicular component of the electric field, E perpendicular above, is not the same as E below. And in fact, there is a discontinuity here, which is proportional to the surface charge density at any point. Okay, so E above, the perpendicular component, if you look at the difference from E below, that's proportional to the surface charge density. Okay, so if the surface is not charged, yes, these two should become equal to each other. But as soon as you have certain charge distribution on the surface, then the perpendicular components become discontinuous. Okay, so this is something we use when we talk about conductors, when we talk about how, when we calculated the surface induced charge for, let's say, the case that we had charge induced from a point charge on the surface of the conductor. For those cases, we use this discontinuity of the electric field to calculate what magnitude of surface charge density we have. Okay, so if you remember when we look at the image charge method in chapter 3, we kind of use this one to calculate what is the density of the induced charges. Okay.
I think I know what the example is. What we're talking about. It's on page 88 on boundary conditions.
Yes. Yes, I'm looking at the boundary condition. It's in chapter 2, and we used it in chapter 3 as well. Sounds good?
Yep.
Yes. Any question?
What do parallel arrows represent?
Parallel arrows are the parallel components of the electric field. Okay,
Oh,
so
I see.
electric fields are vectors, right? You can break them on into two components, one component being parallel to the surface, the other component being perpendicular to the surface.
Oh, gotcha, gotcha.
The
Okay.
parallel components are always the same, okay? Later on, you will see that in magnetic fields, it's the other way around. In magnetic fields, the perpendicular components are always the same when they are passing through a surface carrying current, but the parallel components show certain discontinuity.
Sounds good, thank you.
Yeah. So in the next course, Physics 411, our starting point is magnetostatics. And you see the electric and magnetic field have certain properties that are exactly opposite to each other, okay? And that comes from all, like if you look at it mathematically, electric field has divergence but no curl, magnetic field has curl but no divergence. So certain properties are kind of switched. And this is one of those things, like interesting comparison between magnetic and electric field. Okay. Oh my God. I keep talking and talking, and today is one of those days I forgot my water bottle. Okay, I'm very dehydrated. Okay, so if there's no question, I want to move on and talk about conduct. Oh, we have work and energy as well. Okay, so we have like 20 minutes. Okay, so I'm going to quickly talk about work and energy and then move on to the conductors. Okay. So in the section on work and energy, we look at how we looked at the energy it takes to bring point charges together. Okay, so imagine we have a collection of point charges, Q1, Q2, and so on, okay? And one question is, how much energy it takes for us to bring these charges together, okay? You can imagine if all these charges are positive, okay, and if they are positive, they keep repelling each other. So it really takes energy that someone needs to push them and bring this collection together. If some of them are negative, of course they're attractive, so it releases some energy as well. But overall, we looked at what kind of energy it takes to create this, okay, and then we moved on and we look at the energy that takes to create a continuous charge distribution, okay. So to look at this, our method was, we first look at the Q1, we said let's bring Q1 from infinity, and then bring Q2, and then bring Q3, and so on, okay. And we formulated the work, and this is really mechanical work. We integrated f dot dx, okay. So I'm skipping those parts, but at the end, we could write that in terms of W is 1/2 summation over Qi. Qi is the charge of the point charge number I times VRI. And this is the electric potential created by all charges at the position of the charge Qi, okay? And it means that exclude the effect of the charge Qi itself, but includes all other point charges, okay? So we had this 1/2 QIRI, and of course, I runs from 1 to n, the total number of point charges we had, okay? So if you see a problem, let's say we have 4 point charges sitting on a square, That is plus Q minus Q minus Q plus Q. If you see something like this, you know how to calculate the energy of this collection. Okay, you have 1, 2, 3, 4 charges. This summation runs from 1 to 4, and then you look at each of the charges and then look at the potential created by the 3 others on this position. Okay, so let's say you look at the plus Q and then you look at what is this potential created by the rest of them, which are the 3 others at this position. Okay, and you repeat the same thing on all 4 charges. Okay, so I will run from 1 to 4 for these cases. Sounds good?
Professor, is this problem 2.31?
I guess so. I think this is one of the problems in the textbook. I don't know exactly what problem is. I don't have the textbook right here, but this is a very classical example. Okay. Another classic example of this is, let's imagine you have an infinitely long charge distribution. You have plus Q, negative Q, plus Q, negative Q, okay? And that goes all the way to infinity, from this side all the way to infinity. And again, with this summation, you can calculate what is the energy of charge distribution. Of course, this integral then runs over the infinity, but you will have terms that are decreasing, and then you have a summation like this. Sounds good? Same concept, different mathematics. Yeah. So then the question was, what if we have continuous charge distribution? Okay, so I'm going to get rid of this. If we have continuous charge distribution, this work, okay, that instead of being a summation, it becomes an integral 1/2 rho v d theta, okay? So any small volume here, d theta, okay? And imagine the charge density here is rho. Rho times v dot theta gives you the energy of the charge distribution. This integral very specifically should run over the volume that we have charge distribution, okay? It's okay to extend this to infinity, knowing that if you move out of this charge distribution, there's no charge density, so rho drops to 0, okay? And if you remember, with quite a bit of mathematics, we showed that this integral is at the end equal to epsilon by 2 integral of electric field to the power of 2 times d theta, where this integral runs over all space. Okay, and the idea is that if we have any charge distribution like this, of course it creates electric field. Okay, if it's, let's say, positive, it creates certain electric field in the space that in fact runs all the way to infinity, okay? So the energy of this charge distribution, of course, can be calculated by this integral, but also can be calculated by this integral, where we integrate over the electric field created by this inside and outside all the way to infinity, okay? And later on, you will see this is more useful way because it carries a nice meaning that electric field carries an energy density. Okay, so anywhere in a space that we have electric field, we can associate certain charge density, certain energy density to those electric fields. Okay, so we did one example, that's example 2.9. Where we looked at the spherical shell carrying the charge density of sigma. We looked at the W and 2 solutions, okay? And both solutions are in the textbook as well. One of them was integrating directly on where we have charge distribution, the integral of sigma v dA over the surface of the shell. The other approach was integrating epsilon by 2 integral of electric field to the power of 2 d theta over all the space. In the second approach, you look at the electric field created by the sigma. There is no electric field inside, but outside there's electric field that extends all the way to infinity. We look at e to the power of 2 and this integral. Eventually, we found that these two approaches both give us the same answer, as they should. Sounds good? Okay, we have about 15 minutes. So what I want to do is, I want to skip the part on conductor and capacitor. Okay, I'm skipping this part and I'm gonna move on to chapter 3 so that we have a little time to look at those things as well. If I have more time, I will come back to this. So on chapter 3, I want to mention two topics: image charge method and then the other one is separation of variable. So method of image, can you tell me what is the basic idea for that method? And that
When
has
you have a
a very basic idea of uniqueness for the solutions of Laplace's equation.
I was gonna say you just project the charge onto the grounded plate,
Mm-hmm.
and as if there was a opposite charge of that.
Yeah, that's exactly the method. And now, why is that correct? Why that method works? The idea is this: if you can somehow come up with a solution of the Laplace's equation that satisfies the equation and also satisfies the boundary condition, that is the solution, right? So with the method of image, it's very special. We say that if you are near a conductor that is grounded, okay, we can always use an image exactly the same way that mirror creates image. And for any charge, we can assume there is another charge on the other side, right, that carries the opposite charge. And then we looked at the potential created by this type of charge settings, okay, positive and negative, and we saw that it satisfies Laplace's equation and boundary conditions, right? So if you come up with that solution, that is correct. Okay, so that's the idea, okay? So for this is a very classic problem that we have a charge near a flat surface, okay, and this is a grounded conductor. If we have charge positive Q, okay, near this surface, it creates certain electric field. Okay, the field lines are somehow similar to this. okay? And we said that the situation here is very similar to the situation that here we do not have anything, but instead we have a charge of negative Q on the other side, okay? And we know the field lines created by these two charges actually look like this. And now we project that the electric potential and electric field created at the upper half of the space here, the same potential can be applied here in a way that it satisfies the Laplace's equation, of course, because it's a potential created by 2-point charges and satisfies the boundary conditions, okay? So we had two boundary conditions here. One, the boundary condition was at infinity, V should be 0. Number two, on the surface, instead of writing on the surface, I'm going to say at, let's say z equals 0, okay? Imagine this is z direction. Okay, at z equals 0, potential should be 0 as well, okay? And with these 2-point charges, both of these boundary conditions are met. If we go all the way to infinity, potential is 0. If we stay on this line of z equals 0, which is right between the point charge, the two charges, potential becomes 0 as well. Potential created by positive completely cancels out the potential created by the negative charge, okay? If we are in the midline between them, okay? So these two charges satisfy the boundary condition, satisfy the Laplace's equation. So for the half of this space above the conductor, we can say the electric potential are the same in this case and in this case. Sounds good. So as soon as we have the electric potential, which can be calculated from this, we can look at the electric field, we can look at the electric field on the surface and whatnot, okay? So for the potential here, V, which is a function of x, y, and z, okay, so I'm assuming z is this direction, and this is x, okay, so, and this is x, okay? So now if you look at this, 2-point charges are simply 1/4 pi epsilon 0 positive q divided by r plus minus plus negative q divided by r minus, okay? So what is r plus, what is r minus? That is, if you're standing at this point, the distance from this is r plus. The distance from the negative charge is r minus, okay? And they can be written in terms of x, y, and z, okay? So if this is, the distance here is d, same as here being d, r plus is square root of x2 plus y2 plus z minus d2, all under square root, and r minus is the square root of x2 plus y2 plus z plus d2. Sounds good? So if you plug back here, you technically have the potential as a function of x, y, z, okay? What is the electric field? Electric field is simply the negative of the gradient of the electric potential. And one of the nice things we did in this example, from the electric potential on the surface, and in fact from the derivative of the electric potential on the surface, we could calculate we could calculate the profile of the induced charge density. Okay, if you remember, previously on the boundary condition problem, I said we always have discontinuity in the vertical component of the electric field, okay? So what does it mean? That means V above minus E below is 1/epsilon 0 times sigma. For cases like these, that we are on the surface of a conductor, there is technically no E below because there's no electric field inside the conductor. So E above should be equal to 1 over epsilon 0 times Q. Okay, E below, that term is just simply 0. What is the normal component of the electric field just above? We can calculate from the derivative of the potential. Okay, so E above, perpendicular component is negative of dV over dz. Over dz because vertical component z, and if we want to look at right on the surface, we need to look at it at z equal to 0. Okay, so putting back that one here, we can rewrite it as negative of dV over dz is 1 over epsilon 0 q. So if you have the potential calculated here, by taking this derivative, we can calculate the surface charge density, which is the charge induced on the surface by this positive charge, okay? And that's a very nice thing. If you remember, we did integrate over this surface charge, and we calculated that the total charge brought up here to the surface of the conductor is equal to the negative of Q, okay? There's a profile. Density is higher here, lower at the end. We could actually, you can even qualitatively show the magnitude of Q, the magnitude of induced charges as a function of distance from this point, okay? So you will see you have higher surface charge density right here because it's the closest point to the positive Q, and as if you go further away, the density drops, okay? But the total charge, if you integrate it, should be equal to the negative of Q. Okay, that means if you have a metal surface, you bring a charge, okay, it's going to attract negative charges. The total amount should be equal to the charge that you brought to the surface, okay? I like that example. That's nice. Sounds good? Okay, so looks like we're out of time here, okay? So what I suggest you to do to prepare for the exam, okay, is this. Read the textbook, okay? Read the textbook and focus so much on the examples that I did in the class as well. So all those examples I did in class are from the textbook, okay? So one thing you can do is that you can watch my videos and read the textbook at the same time so you can really catch what examples I did in class. That's one way. But make sure you can reproduce a lot of those examples. So one example like this, make sure you can reproduce this, okay? And if you understand all those examples, the problems you will see on the exam are very related to those examples, okay? They are not exactly the same, obviously, okay? But I assure you, if you understand the examples, you understand the problem, you can do the question as well, okay? And for the separation of variable, we did 3 examples, right? For the spherical coordinates, for Cartesian coordinates, okay? Make sure you read the example number 1 and 2. So let me tell you, I didn't get a chance to review that today, but so if you look at page 131 of the textbook, okay, that's where the separation of variable for Cartesian coordinates starts, okay? And right at the beginning of that chapter, you have example 3.3, okay? Make sure you completely understand that one, that example. So that is the basic of the separation of variable, okay? I would say that's not an example that's really fundamental of the separation of variable. It has several pages. Make sure you understand that one as well. And you can do example 3.4 and 3.5 as a practice as well. Okay, but example 3.3, read that very carefully, understand that very well before coming to the exam. Okay, so everybody, I assume you have textbook, okay? There's PDF version as well. So it's you. Chapter 1, I would not give you any problem specifically being on calculus, okay? So you will see physics problems, but the topic of the chapter 1, you want to understand the divergence theorem. You want to understand the fundamental theorem of the fundamental theorems of the calculus, okay? But don't expect any calculus problem on the exam. You will have 3 physics problems in which you will use calculus as well. Okay, so that's the idea. And that's why I reviewed 2 and 3 here. Sounds good? Again, if you read something, anything unclear, if you don't really understand, feel free to just send me an email, okay?
So then basically the test is going to be on chapters 2 and 3, but with calculus in it, of course, because they rely on it.
Yes, so that's it. I wouldn't phrase it that way, because if I say chapter 2 and 3, you completely forget chapter 1, and then you might need something from chapter 1 to really do chapter 2 and 3. What I say is this: there will not be a specifically calculus problem on the midterm. Okay, you will see physics problems. Sounds good?
Sounds good.
Perfect. Okay, guys, work hard. Come back on Thursday morning and you will be fine. Okay, bye.
Question, Professor,
Sure.
before we go. The format for the testing is going to be the same as the quizzes, where we do a video and then turn it in on.
Yeah, very similar to the, you don't record your video, okay? There's no video recording. You just write papers and then take pictures, send it to me.
Okay.
Okay, you don't need to record videos, because those videos will be very long if you want to do 3 problems. Okay.
Got it.
Professor, spherical coordinates will be something to study as well for separation of variables.
So some of the problems, you know, when you do when you calculate the electric field potential and things like that, you really use the spherical coordinates. So you want to review that from chapter 1 so that you're comfortable choosing the infinitesimal area or infinitesimal volume and carrying the integral over that one. Any more questions?
Professor, could I talk to you after?
After, yes, you can talk to me after. Sounds good. Okay, so if you want to leave, you can leave. Those who want to talk to me after class, they can stay online.
Thank you, Professor. Have a good day.
Thank you. You guys have a good day.
I just had one quick question.
Sure.
We're going to be submitting the midterm through the student email to you or through the critic?
Through the student email.
Okay. I was just curious, just so.
Yeah.
Okay.
Through a student email, you can send me PDF files, attach it, okay? If you find you have too many pages, hopefully not, because the problems I'm giving you, each of them are at most 1-page solution. None of them are super long, okay?
Okay.
So if you find you have 10 pages, again, hopefully not, then you can upload it on Dropbox and send me the Dropbox.
Okay. Usually I just put it on a Word document so you can look at it.
Word document is fine as well. PDF is fine. JPEG is fine. As long as it is legible, good quality, that's fine. Any format.
Okay. If it's okay, I'll just send you the photos of it because that'll save me a lot of time.
Yes, it's fine to send me the photos. Yes.
Okay. Thank you so much.
Thank you.
Bye, Professor.
I was wondering, why didn't you make the R plus and R minus symmetrical on the?
Why didn't I do this symmetrical intentionally? Because R plus and R minus actually cover the whatever space and whatever point in the whole space that you want to cover. Okay, it's not only for symmetric cases. You can choose a point here and still you can calculate, let's say, the potential based on what is R plus distance from here to here and R minus this.
Oh.
It doesn't need to be symmetric. R plus and R minus doesn't need to be symmetric.
So that relates to, you know, the homework problem we had where we had to do where we had like the circle and we had to make a triangle.
Yeah, you should remind me these problems.
Like this. But I didn't know which one was correct. Like, is this correct graph or is this the correct graph?
Oh, so listen, both of them are correct in the sense that what you want to calculate, okay? If you want to show that electric potential is zero on the surface, okay? So here you have the Q prime, right? And here you have the Q. Sounds good? So at any point, you can actually find the potential, okay? It doesn't need to be on the surface. But if you want to show that the electric potential on the surface is zero, then what you want to do is that you should only focus on points that are on the surface of the conductor, okay? So you should forget about this and just look at the points on the surface and show that the potential is zero. Likewise, if I want to show that this charge setting satisfies the boundary condition number 2, which tells me at z equals 0, v should be 0, then if that is the goal, I should really focus on this and say this is r plus, this is r minus. Here specifically, because of the symmetry, r plus is equal to r minus, and then I should look at the potential here. In this case, the potential is obviously 0 because all the symmetry and being positive and negative here, okay? So in this case, it's very obvious that the potential on the surface is 0. For this case of the sphere, it's not obvious. It actually takes like 3-4 lines to show that actually potential is 0 on the surface.
So what I don't understand is, because I thought when we're doing the method of image charges or images, we're like it's supposed to be symmetrical or like across the boundary where you have it, but like in that, you know, with the sphere, it's not symmetrical.
This one is not symmetric, no. No, it's very interesting. I can tell you the method of image charges, the way you can think about that is imagine you have really a mirror, okay? If you have a flat mirror, you see picture of yourself exactly on the other side, okay? It's symmetric. If you have a metal ball, what you will see is not exactly, you see someone which is smaller than you, and that's exactly reflected here. The Q prime has a smaller part than this, and not located right at the center of that sphere, somewhere else, okay?
Okay.
And then there are image problems. I think I assigned one of them to you. It's like you have two metal surfaces that are perpendicular to each other. You have the charge of Q. Okay. Again, if you want to think about this, think about mirrors. If you have two mirrors perpendicular to each other, how many images you will see? You will see one here, you will see one here, and you will see another one, which is reflection of the reflection here.
Yeah. Sounds good.
It's
just confusing that I thought the whole reason why we could use it was because of the symmetry, but like then like
not necessarily.
It's not
No, not necessarily.
All right.
And then
Thank you.
in crazy cases, you can have combination of these. You can have one surface, you can have one sphere, and then you can have image of the image. You can have parallel surfaces that you have infinite number of reflection of the reflection, and so on. Yeah, there are crazy cases too.
Sounds like Inception.
Yeah.
All right, thank you.
Sounds good, thank you. Okay, any more question? I think, let's see, Benjamin, you're online. Or maybe he forgot to go offline. Okay, see you later, Victor. Bye.
See you, Professor.